Okay, so numerical methods, and I think we're going to start with talking about the discrete setting. So we have a bunch of Diracs mapped to a bunch of Diracs. So I'm going to start with a special case of this, which involved one of the earliest methods, I guess, for a special case of this was the auction algorithm by Brittany, which it has a really nice interpretation. You write down the variables and sort of interpret them, and then you say, let's hold an auction. And you can watch people bid and see how this ends up solving your optimal transport problem in this setting. So it's not every optimal transport problem, and it's not every discrete optimal transport problem, but it's some of them. So this is optimal transport in the case of okay, we have the same number of Diracs in the source and the target, and they all have the same weight to them. Okay, so mu has the form of a bunch of Diracs that are equally weighted, and nu has the form of the same number of Diracs, which are also equally weighted. Okay, and our goal here is our usual goal, to find some kind of map between them that minimizes a cost function. Okay, so with the same number of Diracs in the source or the target, this is an example of an assignment problem, right? Each Dirac in my source is going to get paired with exactly one Dirac in the target, and vice versa. Everybody in the target gets paired with exactly one person in the source. And we just have to pick this assignment in a way that minimizes this cost. So this is an assignment problem. Okay, so what do we seek? Really, we seek some sort of bijective function, t, that maps from the x space to the, I guess that was a capital N, to the y space. Okay, and then recall we had a dual formulation of this. So we'll just kind of remember that. The dual problem was this, that we want to instead do a maximization problem where we add up ui, right, times, it was mu I, but the mu's are all the same, so it doesn't affect anything. And we add up all these j's. Right, where now our constraint involves the cost function. And we know that the optimal solution of this, right, will be a C dual pair U and V. So if we assume that, we can write this as actually an unconstrained problem. Okay, so assuming that U and V are C duals, we get an unconstrained problem. Okay, so what's the unconstrained problem? We're trying to maximize. Now instead of U, I could write this as the C transform of V. So the C transform of V is a minimum, okay, of the cost minus V. And now there's no constraints. It's just an objective function that we're trying to minimize. Okay, so I'm going to relabel the variables a little bit. Basically, I'm going to be interested, instead of each of these variables, the negative of its variable. It doesn't change the math at all. We can write the algorithm in this form, but what it will do is give us this interpretation that Brittany had when he wrote down this auction algorithm. So when I relabel everything a little bit, I will lend a little intuition into the problem, I think. Okay? But again, you can run the algorithm in this setting. Okay, so if we're trying to build the auction algorithm, I'm going to relabel things a bit. Okay, to build the interpretation from the auction algorithm. This was from around 88. Okay, so how am I going to interpret things? I'm going to think of xi are people. So each I corresponds to a different person. Okay, and the yj are objects that the people want. And we've got to come up with an assignment between them somehow. I don't know, maybe the objects are a place to live or a job or some other object that we're trying to assign to them. But everybody needs one place to live. And we're going to fill up every house, for example. And how are we going to do this? How are we going to decide who goes with what? Well, we're going to let aij be the negative of my cost function in this setting. And by the way, this cost function could be negative. That's fine. So these very well might be a positive numbers here. There's no issue with that. And this is going to have an interpretation. This is the value that person I associates to object j. Okay, so if the object j happens to be close to the place where person I works, he might like that. If house j happens to be in a good school district, person I might like that if he has young kids, and he might not care at all if he's a young bachelor. Yeah, right? So everybody's going to value these different objects differently.
So the assumption is here that you go at an auction and have to leave with something.
The assumption is that we're going to go to an auction and we're going to leave with something. Nobody's left homeless, we hope. All right, so how are we going to do this? Okay, so that was the value. And now what's our goal, really? We're trying to find an assignment. We were trying to minimize the cost function. Now we're trying to instead maximize this value function. So let's find an assignment from between x and y. So remember, an assignment is going to be this bijective function, 1-to-1 onto, okay, to maximize this overall value. Okay, so I'm going to call this v of t, which is, it's going to be, exactly this. But now in terms of a, we're trying to maximize the sum of these a's. Okay, so I wrote down this was my primal problem. I can also do the same kind of thing with my dual problem. Again, I'm going to kind of negate everything and then write down a way of interpreting the negation of all of these things. So let's let mi equal minus ui, and pj is minus vj. Then in this language, the dual problem is no longer a maximization problem, it's a minimization problem. We're going to minimize the sum of my mi's and the sum of my pj's, subject to mi plus pj now being greater than or equal to a. Same problem, everything just gets flipped on its head. We can write an analog of this C duality condition, some sort of A duality that we're going to have. So this is our C dual condition. Okay, that I minus mi is ui, right, which we knew was going to be the minimization of Cij minus Vj. That's the min of minus Aij plus Pj. Okay, so then if I want to solve for m in terms of p, right, again, there's a relationship between m and p. Mi is going to be, okay, minus the min, so that's the max of Aij minus Pj. Right, and then just like before, I can get an unconstrained version of my dual problem. So my unconstrained dual problem becomes that we want to minimize, okay, mi, which is now the dual of p. So that's the maximum over all j a minus p plus the sum of the p's. Okay, I haven't really done anything, right? I just gave new names to everything.
So we're just operating at the discrete level of
This
everything.
is a discrete problem, exactly.
Right, with U and VJ, assuming that they're C duals and then relate them.
Yes, so all I'm doing is saying with this relabeling, let me plug it into what I already knew about, you know, this was sort of our original dual problem that we've studied quite a bit. I'll just plug that in and see what happens. So I haven't done anything. This is like,
No algorithm yet.
there's no algorithm. This was just like middle school arithmetic or something. I don't know. Okay, I did it for a reason, though. I did it for the interpretation. So let's see if we can propose an interpretation for some of these things. Okay, so Pj, we're going to give a name. P is going to be the price of object j. All right, this is the rent for apartment number j or house number j or whatever it is. Okay, so then if we look at, let's see, this quantity comes up, this difference here, Aig minus Pj. We can try to interpret that. So Aij minus Pj, what is that? Aij is the value person A ascribes to object j, and then minus the cost. So this would be like a benefit of person I to person I of object j, right? It's how much he wants it minus how much it's going to cost him. Net benefit. If it's positive, then this is a great object to have. If it's negative, then maybe not. Okay, so we're going to call this the benefit of object j to person I. Now, when we do the optimization, we solve this dual problem, right? Person I is not going to get assigned to every one of these. Only one of these j's he's going to get assigned to. And the one he's going to get assigned to is precisely the one that realizes this maximum here, right? Because our optimum comes from this C dual pair. So if we, kind of know all the m's and know all the j's, and we can decide exactly which object person I wants the most, which object he's going to get. And the one he's going to get is the one he wants the most under this pricing scheme. So we can say the optimum of this dual problem assigns everyone the object that benefits him the most. Okay, and that's true because MI, which decides the assignment, is exactly the maximum of the benefit. And we know when we did these optimal maps before in the context of the dual problem, we defined the optimal map, this optimal assignment, to be precisely the value of y that made us realize this maximum, right? In other words, precisely the value of j that realizes this maximum is how we defined the optimal map, and we proved that that was what actually gave us the optimal map for the optimal transport problem. Okay, so we know that indeed mi is equal to, say, aij star minus pj star if yj star is equal to t of xi. This was the result that we had, that this C duality and using that actually gave us a map and said that actually looking at the dual problem was useful for thinking about the original optimal transport problem. So this M, we're going to call the profit margin. So M is the profit margin of person I under the particular pricing scheme P. Right, we don't know P ahead of time, the pricing. P was one of our dual variables that we have to try to solve for if we're solving the dual problem. But once we know P, we know M, and this is going to be the actual benefit that person I ends up with when we solve this assignment problem. Okay, and this condition here, this condition is known as complementary slackness, which we're going to try to relax a little bit. So complementary slackness, or CS, so I don't have to keep writing it, is precisely this condition, that MI, let me put it this way, the maximum over all j of A minus P is attained at precisely this value of J star that we get from the map. Okay, this was the nice relationship we had between our primal and dual problems. So I guess Brzeska's first idea here was something that we do all the time in numerics, is to say, let's not enforce this exactly, let's try to enforce this approximately, right? We relax it somehow, we regularize it somehow. We're willing to introduce a little bit of error somehow into this problem in the interest of being able to build an algorithm that we can actually compute the solution to this nearby problem. Okay, so I'm going to talk about how we relax this a little bit, I'm going to use this language of assignments. I've used the word, but let me define it. So an assignment is going to be a set of pairs. It's just going to be the set of pairs of person I with object J that he gets assigned to. Okay, so it's a set of pairs, ij, with both I and j being between 1 and n, such that, okay, for all I, each person gets assigned to at most one place. So there exists at most one j, such that ij is in S. And similarly, for each object, at most one person gets assigned. Okay, so an assignment doesn't have to assign everybody. For a given assignment, somebody might be homeless, some house might be empty, which is not the state that we want at the end of the day. What this is a list of pairings that we've decided. Person I goes with this object, and person number 2 goes with that object, and at least a few of these, or maybe not. Maybe it's an empty assignment. But it says there's no repetition. Then what we want is not any old assignment, but we want a complete assignment where everybody gets assigned and every object gets assigned. So a complete assignment is an assignment that consists of n pairs. N pairs, there's no repetition, which means an assignment, a complete assignment, is equivalent to having this bijective map between my xi's and my yj's. So another way of writing the complementary slackness condition in this language is that the maximum overall j of aij minus pj equals aij star minus pj star when I and j star belongs to S. And, okay, we can certainly write down assignments for which is not true, but it will be true for the optimal assignment. We know it'll be true for the optimal assignment because we know that in the optimal assignment we have this C duality. So it might not be true for every assignment, but it is certainly true when S star is the optimal assignment. Okay, so let's try to relax this a little bit and say, trying to do this exactly might be hard. You know, okay, in principle, we can do assignment problems exactly, right? Because you could go through and here's a list of people. How much do you value each of these objects? Okay, how much do you value each of these objects? And then we try all the different possible combinations, and then we find which one gives us the maximum value of the maximum overvalue. That's possible in principle, but it's a combinatorial problem, right? There's no way you can do that in practice. So let's relax it. For epsilon greater than 0, we're going to say that an assignment satisfies epsilon complementary slackness if the assignment gets us within epsilon of this condition, of this maximum. So if the maximum, okay, we're not guaranteed to hit this maximum, but what we want is to get within epsilon of it So we should be able to get at least up to the maximum minus epsilon with our assignment. Okay, when ij star is an element of the assignment. Right, so in other words, in the assignment, this is the benefit that person I ends up receiving, right? Okay, it's not his maximum possible benefit, but it's pretty close. It's within epsilon, if epsilon is small. Is that okay so far? Yeah. It doesn't have to be S star. So here, let me put this. An assignment S satisfies epsilon complementary slackness. So here I'm using F star as really the optimal assignment, the optimal transport solution, if you like. And this is just some other assignment that may not be optimal, but hopefully it gets close. Okay, so what is this bias? Okay, first of all, we'll come back to this. Is this an easier condition to actually fulfill in practice? You know, is this easier to build an algorithm for? I mean, the crude answer is probably yes, because there's probably more assignments that satisfy this condition than this condition. So maybe it's easier to stumble on one. Hopefully, we're not going to just stumble on one. But what does it really get us? If we get this condition, are we in some sense close to the optimal assignment? All right, so let's try to think about, first of all, if this is a reasonable condition to look for. So what does this bias? Right. And remember, you know, the p's are unknowns ahead of time, right? So we find an assignment and we find a pricing system that gives us that, this. Is there a guarantee that that's anywhere close to the pricing and the assignment coming from our optimal transport plan? Because p is another unknown. So let's first think about the optimal guys. So S star and P star are optimal. For our dual problem. Okay, optimality implies complementary slackness, right? Optimality implies we have this C duality in our dual variables. So we certainly have complementary slackness here. So we should be able to say something about the value of our dual problem. So remember, I wrote this unconstrained version of the dual problem, right? It depended only on doing this minimizing over this vector p, right? And from p, we can get m. So this was our objective function. So let's see, call it the, let me write it this way. This is the objective function with the optimal p star. So this was, okay, our duality relationship. And then we had to add up all the p's. So these are adding up all the m's, and these are going to add up all the p's. Okay, this maximum is obtained precisely for the pairings that show up in this assignment. So this I can write as, all right, A ij star minus pj and then I still have this. Okay, so where, okay, for each I, J star is implicitly a function of I here, right? I and J star belong to this optimal assignment. Can I simplify this? Could I get rid of some of the p's? Yeah. So it seems like here I'm adding up all of the p's. Here I seem to be subtracting some of the p's. So which p's can I get rid of? K equals j. Okay. Right now we're cycling through different j's, right? So I didn't write this here. J is implicitly a function of I, right? So which p's can I get rid of? Let's ask it another way. So we're looping through all the values of I, right? How many values of j, different values of j, are we going to loop through here? What's that? N of them, yeah. So, and that's all of them, right? We said our optimal assignment is a complete assignment, right? That means every I shows up once in it and every j shows up once in it. So these j's are certainly in a different order than these k's. Not certainly, but they're probably in a different order than these k's. But they're all here, right? So really, I'm, with a minus sign, adding up every one of these prices exactly once. And here, I'm adding up every one of these prices exactly once. So this is, in fact, nothing but adding up my a's. Right, and again, ij star is belonging to this optimal assignment. This sum, we've seen this sum before. This was basically exactly the objective function for our original primal problem, right? We had our dual problem that involves adding up these m's and j's, adding up our u's and v's in our original optimal transport dual problem. The primal problem was adding up either theCij's, or when we transformed, it was adding up the Aij's. So this is the value of the objective function for this particular assignment, right? And we know that this optimal assignment is, in fact, going to be the assignment that achieves the optimum in this objective function. This is really the maximum overall, the maximum possible sum of the Aij's, right? So this is indeed the maximum of the Aij's over different complete assignments. Oops, with ij belonging to S. And this was the thing that we called the value, the overall value of this particular assignment on this particular assignment S star. Okay, this hopefully isn't too surprising a result. This just says that the value of the dual problem at its optimum, at its minimum, I guess, is equal to the value of the primal problem at its optimum, right? Oh. And that's something we expect for these type of linear programs. Right? And it's something that we've seen before, that the primal problem and the dual problem are looking from different directions, but at the optimum, they hit the same value. Okay, so that's the optimal map. Now we want to find out what's going to happen if we don't use the optimal assignment, but we use some other assignment that doesn't quite satisfy this, C duality, but it comes close, and it satisfies this sort of epsilon complementary slackness. You may ask a stupid question. Yeah, I like stupid questions.
Have we gotten to the algorithm at all so far? It just seems like we're interpreting things.
We're interpreting things. Once we've really interpreted things, then we can build an algorithm.
Okay.
So yeah, the algorithm, the goal of the algorithm is going to be to try to come up with an assignment that achieves epsilon complementary slackness. But what we want to know before we build the algorithm is that actually useful to come up with something that achieves this?
Okay.
So step one, I'm going to say that, yeah, actually, if we can achieve this, then we're pretty happy with our assignment. And then step two, we're going to hold an auction. Okay, so let's now let S be any complete assignment. Okay, that satisfies this epsilon complementary slackness with the pricing scheme P. Okay, because we can't talk about complementary slackness unless we have some values for the P's. Okay, again, we can write down the value of the dual problem. Right, same as it was before. So we have our MIs, which was in terms of P's, A minus P, and then we added up the P's. Okay, now again, I want to be able to drop the max here and just say this is I with a particular value of j in here. Now I can't do that exactly, but I can get close, right? I can write the maximum not equal to this, but less than or equal to this plus epsilon. Okay, so I'm going to write this as I equals 1 to n of aij minus pj. Again, these j's depend on I. Okay, but now not only that, but also we're going to need a plus epsilon. And we add up the p's. Right, with I and j being elements of the assignment. Does each column sum to 1?
How are you moving the epsilon inside?
How am I moving the epsilon inside? So the epsilon is still inside the sum.
Oh.
Right, all I did was,
Gotcha.
yeah, no, the epsilon is still inside the sum. All right, this was a complete assignment. So just like before, all the j's are going to be represented here, right, in some order. I don't know what order, but they're all there, which means I'm adding up all of the different p's here with a minus. I'm adding up all the different p's here. So again, those are going to cancel. So what am I left with? I'm left with, well, the sum of my a's under this particular choice of assignment. And then I have, okay, the p's cancel. I have epsilon in here n times. So I'm going to get plus n times epsilon. Again, this is the value associated with a particular assignment, right? So I've added up all the IIJs under this assignment, and this is exactly what I called the value of assignment S, which is not optimal necessarily, but it's something, plus n epsilon. Okay, the dual problem was a minimization problem, right? So that means that when I put in the optimal value, this value here is going to be less than or equal to this value here, right? Because that was optimal. This is not optimal. Okay, so we know that the dual problem, the objective function for the dual problem computed at p star is certainly less than any other p. Okay, and if I substitute in these values, that means that the value of S star is less than or equal to the value of S plus n times epsilon. So what are we trying to do? Overall, we're trying to maximize value, right? We're trying to come up with some sort of assignment that makes everybody as happy as possible. We're trying to maximize this value. So this is the maximum possible value we could ever come up with. Now we've come up with a different assignment that's not optimal, but it satisfies this epsilon complementary slackness condition. And what this says is that, okay, it's not optimal, but the value is pretty high here, right? We're not optimal, but we're within n times epsilon of the optimal value. So V of S, if S and P satisfy epsilon complementary slackness, then V of S, right, just writing it a different way, the value associated with this assignment is going to be within n epsilon of the optimal value. Okay, and if epsilon is small, that means we get closer and closer to the optimal value. So that's not necessarily a solution of the optimal transport problem or this optimal assignment problem, but in some sense we're getting, in this setting, the value of the assignment as high as possible. In our optimal transport setting, we're bringing the cost arbitrarily close to the minimal cost. There's a special case that Prosecco was interested in. So in his special case, actually you can do this. You can do this in general for this discrete problem. It's easier to see for this special case. In the special case, the values of Aij are all integers. You can do this actually even if they're not all integers, because there's only finitely many different possible values, so they are going to take on a discrete set of values, right? Because there's only n squared different values of Aij. So what happens here? Let S be an epsilon complementary slackness satisfying assignment, but not optimal. So if Ij belongs to this non-optimal thing and Ij star belongs to the optimal assignment, then certainly the value for our optimal assignment is going to be less than, strictly less than, the value of any non-optimal assignment. This is J star. No, we're trying to maximize the value. This is J star. Okay, so this is the maximum possible value. If S is non-optimal, then this value is strictly less than. Well, what's the difference between these two things? The difference between these two things is not 0.1, for example, right? Because A only takes on integer values, right? So the difference between these two things must be at least 1. The value, they have to differ by an integer. So we must have, since these are integer values, and again, what really matters is they just take a discrete set of values. And we have the sum of the aij's being less than or equal to the optimal choice minus 1. And we have a relationship between these things. We knew that, okay, the sum of the optimal things over here was less than or equal to the sum of the non-optimal things plus n epsilon. So this is less than or equal to the sum of the non-optimal things plus n epsilon, and then minus this 1. Which tells us what? It tells us that n epsilon minus 1 must be non-negative. So what did we start with? We started with something that we said, okay, satisfied this epsilon complementary slackness condition. We relaxed the optimality condition a little bit. And then we said it's non-optimal. Well, it's not optimal only if epsilon is too big, right? And the flip side is if epsilon is small enough, if epsilon is less than 1 over n, then anything satisfying epsilon complementary slackness is actually automatically optimal. So we can stick this epsilon into the algorithm, relax the conditions that we should be getting, and then actually still get something optimal at the end of the day. So in other words, if epsilon is less than 1 over n, then this condition actually implies optimality. Any questions? You don't look quite like you believe me.
That's just my thing.
Okay, that's just your face.
Is the epsilon less than 1 over n? I'm assuming you're not just playing with inequality above. I think I missed something when you were speaking before.
Right. So we started by saying, let's suppose we have epsilon complementary slackness, right? And okay. And now suppose it's not optimal. Non-optimal implies this relationship, right? So on the flip side, if we were going to take, say, the contrapositive of it, the reverse of this inequality, which is this, implies then optimality, right? So non-optimality implies this. That means epsilon less than 1 over n implies optimality. So all this to say, this relaxed condition actually makes sense. It's reasonable to try to compute in these relaxed settings, and we will get, depending on epsilon, we will either get close to the optimal value, or we may even be guaranteed to achieve the optimal value. Right? And again, it's not that important that this was differing by 1, and you could have whatever the sort of difference between your aij's is, or whatever the smallest difference between your aij's is, which is something, because it's a finite set. and it would just come up with a different criteria for epsilon. So we want to compute that, and we need an algorithm. So finally, we're going to start talking about an algorithm. And Brzezinski's idea was, let's hold an auction. So the people, xi, participate in an auction. To decide what they received. What do we know? Everybody has to be assigned something, right? Nobody's going to leave the auction until he's received something because he doesn't want to be homeless, for example. So he's going to keep bidding. Everybody's going to keep bidding on something until they finally win a bid on something, right? They're going to try to bid in a clever way, but they're not leaving empty-handed. Okay, and that means at the end of the day we should have a complete assignment, right? Everything will have been purchased. Everybody will have bought something. Okay, so how do we initialize this? Well, we're looking for an assignment. It tells us who bought what. Initially, nobody has bought anything. So initially, we have an empty assignment. Nobody's bid on anything yet. Nobody's bought anything. Nobody holds the high bid on anything. Nothing's happened. And initially, again, nobody's bid on anything initially. So initially, all the PJs are 0. Nothing's been bid on. The price is set at 0. The prices are probably not going to stay there. This pairing satisfies epsilon complementary slackness, yes? Not in a very interesting way, but it is certainly true that I can, do I have the condition written down still? I can never find anything that would violate this inequality, right? So this satisfies epsilon complementary slackness, trivially. Now our goal is to have various rounds of the auction and try to preserve epsilon complementary slackness throughout the auction. So we're going to change the prices. The prices will go up as people bid on things. S is going to tell us who holds the high bid on each object after each stage of the object. And the goal will be to do this in a way that we always have epsilon complementary slackness. Okay, so the prices will go up as people bid, and S will tell us, that's not how you usually spell that, who holds the high bid on each object. And hopefully this will happen after each round. We want to still preserve this epsilon complementary slackness. So we'll need to do a couple things. I haven't written down the algorithm yet, but we'll need to prove a couple things about it. We'll need to prove that we preserve this. And secondly, we need to prove that it terminates at some point in a complete assignment. Once we have a complete assignment that satisfies this, we're done, right? We've got what we want. So if this algorithm terminates, if the auction eventually results in a complete assignment, then we're done. Then we're either within an epsilon of the optimal value, or we've achieved the optimal value, depending on the setup. So each round of the auction is going to have 2 phases. There's a bidding phase. That means, okay, if you already currently hold the high bid on an object, you're not going to bid on something else or bid against yourself or anything, because that would be dumb. but it still happens in real life, but hopefully it doesn't happen here. So anyone who doesn't hold currently a high bid is going to look around at the objects that are available and the prices they're going for, decide what he wants to bid on, and he's going to bid on something because he needs to go home with something. So everybody will bid who needs to. And then secondly, there'll be an assignment phase where we look around and say, okay, for each of these objects that got bid on, who holds the high bid? Okay, you're currently assigned to this object at the end of this round of the auction, and whatever you bid is the current going price for this object. So it was 2 rounds, and we iterate. So let me write down the algorithm now. You've been waiting an hour for me to write down this algorithm. I'm finally going to do it. So here's the bidding phase. Okay, so we're going to loop through all the values of I, all the people that are unassigned. Right? Remember, the assignment tells us who currently holds the high bid on each object. So now we're looping through everyone who doesn't currently hold a high bid. He wants to decide what to bid on. Okay, so he looks around and he says, let's compute the current value or benefit of each object. To person I. Okay, so this we called Aij minus Pj. So under the current pricing scheme, right, the current price of each object is the current high bid on it. He says, okay, I look at how much I want it minus how much it costs. What does that give me? Okay, now I know those, I decide which one I really want. So person I wants object J star that satisfies we get the maximum here. So satisfying Vij star equals the maximum of all Vij. Okay, so he says, person I says, I want to bid on object J star. That's what I want the most. But now I have to decide how much am I going to bid. So the price has to go up. I can't bid under what the current bid is. So now we want to decide how much to bid. So the way he's going to do this is he's going to look around at the other objects out there and say, I know this is the one I want. How superior is it really to everything else that's out there? Are there 100 other things that are almost as good? Well, I'm not going to pay so much for this. Is this like way, way, way superior to anything else out there? Then I want it, and I'm going to bid appropriately to try to make sure I get it. So it matters how valuable everything else is. And it might be that this J star is not unique, and there's a bunch of things that he'd be perfectly happy with. Okay, so let's let Wij star be the value of the next best object. Okay, so Wij star is equal to the maximum over all j not equal to j star of these values or benefits. So it's the second highest benefit. Okay, I got a little extra information. Now I'm ready to bid. So person I bids on object J star, and the bid is okay, so the bid of person I on object J star. Okay, and now it's possible that multiple people will all want J star, so it's possible multiple people will bid on this, but nobody's going to bid on more than one thing at once. So the bid on this is going to be, well, we start with the previous bid. That's our lower bound. Then we say, well, okay, how valuable is this to me really in comparison to everything else? Well, that's going to be determined by the difference between this V and this W, right? If V and W are equal to each other, then I don't really need this over W. If V is quite a lot higher than W, then I'm gonna bid kind of high because I really want this thing. So we're gonna look at the difference between these. Vij star minus Wij star. Okay, so this, again, this could be 0. It could be positive. It's never negative, right? So we're going to get P plus something greater than or equal to 0. He can't bid P, right? He's not going to win if he bids P. So then we're also going to include a plus epsilon just to be sure that the bid goes up. Are we happy with bidding this amount? Yeah. Epsilon might depend on n. We might choose epsilon to depend on n. Certainly we want it to be small. If we're trying to solve things exactly, we need it to depend on n. It's going to depend on, what is your tolerance for not quite hitting the optimal value. If you're saying, I don't really need to hit the optimal value as long as I kind of come within a couple $100 of it, epsilon could be larger. And making epsilon larger, in basically every algorithm you ever do, making epsilon smaller slows things down, right? So there's always this trade-off between speed versus accuracy. Okay, so this is just another way to write this. Pj star plus V. V was the optimal value of this. So this is Aij star minus Pj star. Then minus my W and plus my epsilon. Okay, so this is just another way of writing the optimal bid, which will be useful sometimes when we're analyzing it. So that's the bidding phase. Everybody's looked around, he's decided what he wants, he bids. Now that phase is over, and we move into the assignment phase. Let's decide who has the high bid on each object. So here's the assignment phase. All right, so first of all, for all objects, right, let's let P of j be the set of people who bid on this object. So an object may have received no bids. It may have received lots of bids. We don't know. So, but let's let P of j be the set of people who just bid on object j in this last round. And it could be an empty set. It could be single-valued. It could be multi-valued. We don't know. If it's empty, then we're not going to do anything to this object. He's not assigned to anybody because nobody wants him yet. But the price scheme will have to change before he becomes valuable to somebody else. If everything else starts to become really expensive, at some point people will say, even though it's not as good an object, I'm willing to live a lot farther from campus because I can at least afford rent, right? So if Pj happens to be non-empty, that means somebody, at least one person, has bid on this object. We need to figure out who has the high bid and assign it to him. So we need to update the current price or bid. of object J. Okay, and the new price is just going to be the high bid. So it's going to be the max over all people who bid on this of the bids. And we'll call this bi star j for some I star. I star is just whichever I achieves the maximum. Okay, now it's possible this was the first time anybody has bid on this object, or it's possible somebody previously held the high bid. If somebody previously held the high bid, that I and J are sitting in our assignment, and we say, sorry, buddy, you've lost this object, and we pull them out of the assignment. So if ij currently belongs to S for some I, that means person I held the previous high bid on this object. What are we going to do? We're going to take it away from him. So we remove this pairing from our set of assignments. Person I no longer has the high bid. And now instead we're going to assign this object to this guy who made the current high bid. So let's add this new pairing to S. And that concludes this round of the auction. Right? Everybody's bid. Some objects have been bid on, and we assign them a high bid. Some objects maybe haven't. So nobody's assigned to them yet. And we just keep doing rounds of this auction. Bidding, assignment, keep alternating until finally everything is assigned. Everybody has bid on something. Again, you know, those objects way out there 40 miles away from campus that didn't look very good to you, all of a sudden start to look very good when the price on everything else goes up through the roof. So finally you say, okay, I'm actually going to bid on that. And now we have a complete assignment. And under this particular pricing scheme that we came up with, at the end of the day, you are actually happy with your choice. It did maximize your benefit, because your benefit would be very negative living here right next to campus, because you would not be able to pay your rent. So this is our algorithm. Any questions on the algorithm? So what information do we know at the beginning? We know the AIJs at the beginning. So what we're given is what is the value to each person of each object, right? You know, without reference to any price. Living close to campus is great. It's high value for you because you don't want to commute. Maybe it's lower value if you have young kids and you'd like a little more space and a big yard for them to play on. Maybe that would become higher value to you. So it's the value. We know all these different values. Now we have to decide how much everyone is willing to pay for the objects they want, and that's how we'll decide what we settle on. Other questions? So I'm going to stop a few minutes early today. The next time we're going to actually analyze this algorithm and decide, does it actually produce the complete epsilon complementary slackness assignment that we want? So we'll finish analyzing that and then probably move on to another method for the discrete optimal transport problem.
I have 2 questions.
Okay.
If we already have the matrix AIJ,
Yes.
doesn't that suppose we already have T, the map?
No. So knowing AIJ doesn't tell us that we know T. Right. So A tells us the cost from each I to each J. Now T is going to just tell us a particular map from each I to each J, right? So T goes from each I, it only goes to one of the J's.
Okay, so inverting that matrix technically would give us the map? Or
Inverting the matrix wouldn't give us the map, right? We have to solve this optimization problem. So solving a big linear program would give us this map.
Okay, and the second problem is, does this algorithm or this setup solve any sort of matching problem?
Are you thinking like concrete applications? Or?
For example, it seems like this might solve the stable marriage problem.
For example, yeah, that's one of the examples that I almost mentioned at the beginning. It didn't. But instead of picking a house, we might be picking a spouse mathematically.
But isn't that how like doctors get paired to their
But yeah, for example, doctors getting paired to where they're going to do their residencies or internships. Yeah, so there are concrete assignment problems. Rent is an easy one to visualize what's going on. You're probably not running an algorithm to decide where you live, but although if you're a very good math grad student, maybe you are. But yeah, I would assume that this type of problem is behind doctor residency matching problems, for example, mine to factory type problems.